Today, we're diving into the essential tools and techniques for bending conduit, a critical skill in many trades. We'll be exploring the intricacies of electric and hydraulic conduit benders, drawing from a technical guide on conduit bending. With me is Alex, who's going to walk us through these complex processes.
Thanks, Chloe. Our main objective today is to understand how to use both electric and hydraulic conduit benders effectively. This involves mastering specific performance tasks like bending a stub up to a precise distance, creating an offset to clear obstructions, and forming a saddle bend to cross other pipes, all while maintaining precise clearances.
Sounds like there's a lot of specialized terminology involved here. Before we get into the actual bending, can you clarify some of these trade terms for our listeners? Things like approximate ram travel or springback seem quite important.
Absolutely. Approximate ram travel refers to the distance a hydraulic bender's ram moves to create a bend. Many benders have scales to show this, converting degrees of bend into inches of ram travel, though it's always an approximation due to variations in conduit springback. Springback in simple terms is the amount, measured in degrees, that a bent conduit tends to straighten after pressure is released. For instance, a 90-degree bend might pull back to 88 degrees.
So you have to overbend to compensate for that. What about different types of bends? And what about terms like leg length or ID and OD?
Exactly. We have one-shot shoes, which are large bending shoes designed to make 90-degree bends in a single go. Then there are segment bends, which are formed by a series of smaller bends, each just a few degrees rather than one single bend. These are often made with segmented bending shoes for angles less than 15 degrees per shot. To clarify other terms, leg length is the distance from the end of the straight section to the bend center line or edge, and while all conduit is measured by its inside diameter or ID, the outside diameter or OD varies by conduit type.
That distinction between one-shot and segment bends seems fundamental. And these benders aren't just for small pipes, are they? The guide mentions they're for larger sizes of conduit.
That's right. Both electric and hydraulic benders are crucial for larger conduit sizes. They come with bending tables or software to help determine settings for various conduit types and angles. The most sophisticated equipment can even bend an entire run of conduit to predetermined specifications and label each piece for quick installation.
Given the power these tools wield, safety has to be paramount. What are some of the key safety guidelines outlined?
Safety is non-negotiable. Always read and understand the operating instructions, use the right tool for the job, and never operate tools with damaged or missing parts. It's crucial to watch for pinch points on power bending tools and to work in a well-lit, uncluttered area with enough space for the conduit to move. For hydraulic benders, ensuring connections are clean and tight and replacing worn hoses is vital. Bending shoes and follow bars should be treated as precision instruments, never tossed around, as their condition directly impacts the quality of the final bend.
Those are important reminders. Let's move to electric benders specifically. How do they differ from mechanical ones, and what can they typically handle?
Electric benders work on the same basic principle as mechanical ones, but a gear motor does the bending instead of manual power. They are very convenient for stub-ups, offsets, and saddles, especially when a 120-volt receptacle is available. Specifically, they can make 90-degree one-shot bends in EMT, IMC, or RMC sizes from 1/2 inch through 2 inch.
So it's essentially a powered version. Can you walk us through an example, like making a stub up, since the guide details that process?
Certainly. Imagine needing a 16-inch stub up in 1.25-inch rigid conduit. You'd mark the conduit 16 inches from one end. Then checking the bender's deduct chart for that size, let's say it's 12 3/4 inches, you subtract that from the 16 inches, leaving 3.25 inches. That 3.25-inch mark is where you align the conduit with the bender hook. As you bend, a pointer on the shoe indicates the degree. To account for springback, which the chart might indicate as 5 degrees for 1.25-inch rigid conduit, you'd bend to 95 degrees, so it relaxes to the desired 90.
That's a very precise adjustment. And what about offsets? How do you ensure accuracy there, especially avoiding something called a dogleg?
Offsets use charts for spacing between marks. To prevent a dogleg, which is when the conduit's center line isn't maintained across both bends, you need careful alignment. The procedure involves making the first bend, reversing the motor, turning the conduit upside down, and positioning the second mark. A magnetic torpedo level or an anti-dog device helps maintain alignment. Rebending is possible, but not ideal, as it strains the conduit and can damage coatings.
That makes sense. Now, electric benders have their limits. The guide mentions hydraulic benders are indispensable for larger conduits. What's the threshold for needing a hydraulic bender, and what are their key characteristics?
Hydraulic benders are essential for conduit over 2 inches in EMT, 1.25 inches in IMC, or 1.5 inches in RMC, going up to 5-inch trade-size rigid conduit. The hydraulic pump and cylinder provide the immense power needed for these larger sizes. They are a significant investment, so proper maintenance, especially of the pump, cylinder, and hoses, using only approved hydraulic oil if refilling the pump, is crucial to justify their cost.
The guide specifically warns about dangerous pressures with hydraulic benders. This really emphasizes the need for proper training and caution.
Absolutely. Operating a hydraulic bender requires proper training and extreme caution, often even working with a bending partner, due to the tremendous power they generate. In terms of operation, hydraulic benders also use one-shot and segment shoes. One-shot shoes can form a full 90-degree bend without collapsing the pipe walls. Segment shoes, however, are shorter, with a radius less than 90 degrees, so a 90-degree bend requires multiple smaller bends, sometimes as many as 30, to achieve a smooth radius.
It sounds like precision and patience are key. What about bending rigid aluminum conduit? Are there special considerations for that material?
Yes, rigid aluminum presents unique challenges. 2 pipes from the same bundle can bend differently, and it's prone to wrinkling and scoring. One-shot shoes can even dig into the pipe. The guide suggests applying petroleum jelly or a lubricant like WD-40 to the shoe to allow the pipe to slide and prevent scoring. It also helps with removal after bending.
That's a practical tip. So, once you have the right bender and understand the material, how do you actually measure and execute these segment bends accurately, especially for a 90-degree bend?
For a 90-degree segment bend, you first need to determine the developed length, multiplying the bend radius by 1.57. Then you decide on the number of bending shots, preferably an odd number for even distribution around the center mark. The guide gives an example of calculating spacing for 15 segment bends, each 6 degrees to reach 90 degrees. You mark these points, clamp the conduit, attach a degree indicator, and bend 6 degrees at the first mark, compensating for springback at each shot. Then you move the support and continue, bending 12 degrees at the second mark, and so on, until you reach 90 degrees.
That's a meticulous process. And how do you measure these small angles during the bend? The guide mentions a few methods.
There are 4 main ways. The bend degree protractor hooks onto the pipe, and you rotate its face to the desired scale. The magnetic angle finder is placed on the stub end, indicating degrees per bend, requiring careful adjustments for springback at each shot. The amount of travel method calculates the ram travel needed per shot. Finally, the number of pumps method relies on a consistent number of pump strokes to achieve a specific angle, though it's less precise due to pump condition variability.
It sounds like each method has its pros and cons, but they all demand extreme care. What about concentric bends, where you have multiple parallel runs of conduit?
Concentric bends ensure multiple conduits bend smoothly in the same direction, maintaining consistent spacing. You calculate the innermost conduit's bend first, then add the outside diameter of that pipe and the desired spacing to find the radius for the next. Each successive bend will have a larger radius and therefore a greater developed length, but they all receive the same number of segment bends to maintain concentricity.
That's an elegant solution for parallel runs. And for the ubiquitous offset bends, how are those calculated and performed to clear obstructions?
Offset bends involve two equal bends, typically less than 90 degrees, made a specific distance apart. You determine the offset height, then use a bending chart or trigonometry to find the degree of bend and the distance between the two bend points. For example, to make an 18-inch offset with two 45-degree bends, you'd multiply 18 by 1.414, the cosecant for 45 degrees, which gives you about 25.45 inches between the bend marks.
So you're using geometry to ensure the conduit clears the obstruction precisely. Finally, saddle bends are for crossing over pipes. How do those work?
Saddle bends are for crossing obstructions like other pipes or I-beams. A common three-bend saddle uses two outer bends and one center bend. For example, to cross a 3-inch water pipe with a 1/4-inch clearance using 2-inch rigid conduit, a chart might indicate two 15-degree outer bends and a 30-degree center bend spaced precisely apart. You would mark these points, make the first 15-degree bend, then reverse the conduit and make the 30-degree bend, then reverse again for the final 15-degree bend. For larger obstructions, over 6 inches in diameter, a 4-bend saddle is recommended over a 3-bend one.
It's clear that bending conduit, whether with electric or hydraulic benders, requires a deep understanding of geometry, precise measurements, and careful execution, always with safety in mind. Thank you for shedding light on these intricate processes, Alex.
My pleasure, Chloe.
If you found this discussion helpful for understanding conduit bending, consider sharing this episode with someone who might also benefit.